Hello, today we're going to be doing standard 5.4, which is on time evolution of the non-stationary wave functions. And we're going to be doing problem 5.9 out of McIntyre. The question here states, a particle in an infinite square well has the initial wave function psi x0 equal to a times x over l cubed minus 3/2 x over l squared plus 1/2 x over l. And this is going to be in the interval 0 between 0 and l. So the length of our square well is L, and it'll be 0 elsewhere. We're going to find the wave function at a later time, so we're going to find the time evolution, the probabilities of the energy measurements, and then the expectation value of the energy. It's the expectation value of the Hamiltonian. So in order to complete each of these desired goals, we first need to normalize the wave function, of course. To do this, we can just set this wave function, the modulus squared, take the integral and set it equal to 1. Now when we do that and solve for a, it turns out that a is equal to the square root of 840 over L. And using this, we can then find all the desired things we need to find the time evolution probabilities and expectation values. So from here, we first are going to perform the overlap integral to calculate the expansion coefficients. So we take the position representation of this inner product here between the arbitrary energy eigenstate and our state psi. And we have this integral here. Then when we plug in our energy eigenstate here, and then we plug in our new normalized state from above, the initial condition here, or the initial eigenstate. Yes, the initial state, sorry, not eigenstate. But when we perform this integral here and evaluate at the bounds, we get this nice thing right here. Root 420 over n pi to the 4th times L cubed quantity times 6n pi L cubed plus 6n pi L cubed times cosine n pi. And now noticing here that we have a cosine n pi, we know we're going to have some alternating term. We're going to have a different value for both the even and odd terms. This is because cosine alternates between positive and negative as n alternates between even and odd. So here we go. We collect all our terms, pull things out, cancel things out, and then evaluate. We get 12 times root 105 over n pi cubed. Then this will be times 1 plus negative 1 to the n. So we note here that when n is odd, we'll get a negative 1 plus 1, which will give us 0. So we're going to get 0 when n is odd. Then we're going to multiply this whole quantity by 2 when n is even, because we'll have 1 plus 1. And now that we have this, we have Cn is equal to 24 root 105 over n pi cubed when n is even and 0 when it's odd. So using these expansion coefficients, we can now find the time evolution and probabilities that we desire. And the time evolution can be represented with the following wave function, which is that psi of x of t is equal to the sum from n equals 1 to infinity of our coefficients here times the eigenstate wave functions, times e to the negative I ent over h bar. And now we have both the wave function piece, the eigenstate wave function, and our coefficients. So we can plug this in, and we know that the sum is 0 when it's odd, so we just have the sum when n is even, times 24 root 105 over n pi cubed, times root 2 over l, sine n pi x over l, times e to the negative I ent over h bar. And that's where our energy is as followed. En is equal to n squared pi squared h bar squared all over 2ml squared. We're going to need this coming up when we start looking at the expectation values more closely. So before we get to the expectation value, we need the probabilities. And these can be calculated as followed. We just take the modulus squared of Cn, our coefficients above, and since we just look at here, we can just square both pieces because it's piecewise. So we could just get 24 squared times 105 over n pi to the 6 when it's even and still 0 when it's odd. And now having all these pieces, we can find the expectation value of the energy, which will be the expectation of the Hamiltonian operator because the energy can be calculated this way. So the expectation value for this can be calculated by summing all the probabilities times their respective values. So here we have the sum from n equals 1 to infinity of the probability of the energy measuring at particular energy eigenstate times the energy value itself. And since once again it's 0 every place n is odd, we just have the sum when n is even, times our probability we just calculated, times the energy value we had above. And now if we factor all the terms out that aren't dependent on n, we have this nice coefficient out front. But the more important part here is that we have the sum when n is even of 1 over n to the fourth. This sum actually has a distinct value, and it is pi to the fourth over 1440. And now if we collect all our terms and cancel things out, we're left with 21 h bar squared over ml squared. And if we note that this is like very close to the form of the energy here, except we're missing a pi squared and missing a factor of 2, we actually get that this is equal to 42 over pi squared times the first energy eigenstate, which is approximately equal to 4.26 times the first eigenstate, the eigenvalue, but energy eigenvalue. This is actually really nice because it can actually let us check if our expectation value makes sense and if it's what we expect. So we should note that if we plug in n equals 2 to this probability right here, that we're going to get approximately like 98%, 0.098. And here we note again that the second energy value is the first excited state. It's going to be equal to 4 times the ground state. And here we have 4.26 times as our expected energy measurement. And this makes sense because we have essentially basically everything here. The probability is loaded into the second eigenvalue, and then we have pieces for the remaining even terms. So we expect it to be slightly above. So that shows that our expectation value has relevance and is correct. And that'll be it. Thank you.